instrumentation, logging, sensors, some sort of sensor to gather data for whatever questions you're trying to answer, or whatever activity you're trying to model and automate. And usually that's some sort of survey, or it could be a weather sensor, it could be anything. But once that data is kind of collected, it flows into some sort of data storage, whether it's a database or it's a data lake or a data warehouse, someplace where you can kind of keep that data in a consistent structure and format, and transform it and do whatever kind of data preparation and work you need to do in this movage and storage. And I think that this is what most people think of as like just straight up IT organization type work for moving and storing. So these are like your network drives, or your databases, your infrastructure associated with all of that kind of work, network devices, web servers, all that stuff. The next layer up, this third layer, exploration and transformation. This is where, after the data engineers have kind of taken these raw data collections from the field, they put them into whatever structure, format, and normalize the data to the purpose that it's serving for that specific analysis. So, converting all the dates to the same format is the most common thing that seems to be done, because, like Europe does, day, month, year, US does month, day, year. Those kinds of things you got to straighten out before you try to run through any sort of like data science algorithm, or any sort of like statistical algorithm. This next level up is where most statisticians kind of live, is in these next two levels, which is basically descriptive metrics, segmentation, clustering analysis, some of the just auto labeling, some of these like core functions of making the data usable and transferable to other purposes. And you could do a whole doctorate program just on clustering analysis methodologies and things like that. And this is also where you would sort of like split your data into your different cohorts, right? You would have your training data set and your validation set, and you would do those kinds of work there. And then the last two layers are really where the scientific testing starts to happen. So you do your A/B testing and experimentation, those kinds of analysis on the last layer. And then the vast majority of data science work never really needs any sort of like deep learning or AI type functions. And if you haven't really done these previous steps where you're doing basic fundamental systematic statistical analysis on this kind of stuff, you probably shouldn't even really be venturing into the AI methodologies yet, because that baseline functionality for doing the A/B testing and hypothesis testing is really how you get your baseline of how you're going to judge the performance of the AI system, which is essentially an automated scientific process at that point. So you've built everything else up to this level. You get it to the point where it's ready for some sort of, what your questions are, what the problems you're trying to solve, what your sensors are, what the levers you're going to pull as a result of whatever the outcome is of these algorithms. And then the AI and the deep learning is really just layering on another level that automates the scientific process that was already sort of happening at an incredibly slow pace at this lower level. So contextually, that's where that's the full picture of the whole data science hierarchy of needs. This process flow that I'm going to get into is really about how you go from this aggregate level and these kind of like cleaning anomaly detection type work, and generate an AI deep learning or any sort of like advanced artificial intelligence or data science product. And there's a number of different kind of roles and responsibilities that could be played by the same person, but the activities associated with those roles still need to be kind of completed. So I'll put this chart in the chat if anybody wants to look at it or reference it at a later date. This is probably the single most valuable tool I have whenever I talk to groups about like data science, projects and initiatives. So with that context, let me pull up the next one here, which is really the full data science process flow for building like an artificial intelligence product. And it goes really from, the initial, a lot of this will look familiar, and this is really more from a business context, but the same applies to any sort of scientific development of any sort of AI solution. And it starts out with really just identifying a product need. So what's the problem we're going to solve for? What is the um, process that we're trying to automate that we think that we can add value to with some sort of statistical gray area math decision making, right? So product need, and I'll just pick an example. We'll just say self-driving cars, right? Just to give some context of all of this, right? So if somebody says, hey, it'd be nice, self-driving cars. So the product need is identified. Somebody came up with that idea. They float it over to the data science guys, and they say, you know what, I think I could do that. That's a realistic thing that could happen. We will use some, convolutional neural nets for image classification and risk analysis. We'll use radar data for, distance identification and incorporate that into the steering algorithm. They come up with an idea. And they kind of come up with also a space of data that they think they're going to need in order to um, generate the need for the input of the algorithm to generate the functions that then provide an output, whatever levers, steering wheel, needs to be turned and by how much. And so they float this data set definition and what they're going to need for that algorithm development over to the data engineering organization. And usually the data engineering organization is a separate skill set than the data science team, believe it or not. When you talk to data scientists, they think they do all the data engineering. But there's a whole nother level of processing and development that gets done even before it gets to them, usually in a good organization. And the skill sets are very, very different. And uh, yeah, if you don't have a data engineer incorporated into your development process, a lot of times what you'll get is these really back front end heavy transformation processes that are happening within your data science functions, which are burdensome to the system, and also like just generally it's a waste of skill and talent when you have a statistician with a data science background working on transformations, aggregations, and normalization of data. So hand that off to a guy who specializes in that in the data engineering group, and let them do the data exploration and assessment of whether or not this thing is realistic, while the data science team is working on their KPIs and measurements of success. And that usually the product guy is usually involved as well, from the perspective of like, yeah, no, one of the requirements is that you don't hit small children with your automated car. You also have to not hit curbs ever. That can't be a sensor input for you. You have to avoid that scenario completely. So usually it's the product owner and the guy who comes up with the idea is somebody who's an expert in the area that provides a lot of feedback associated with that process that will save the data scientist a lot of time. Um, Another example, I was once asked to build an algorithm to assess the value of fine art. And I spun my wheels on this problem for weeks, taking in all kinds of crazy data from different places about the space and the competition and the materials of the art. And I spent all this time on it. And then eventually, and I was getting nowhere. I was getting no correlation between the value that my algorithm would output and the actual value of the art as it was sold on Sotheby's or whatever. And so I called an art appraisal person, and he told me the only thing that really matters is the historical context and popularity of that particular piece or that particular artist. And I had to completely rework the entire algorithm. And if I had just included a product expert in that realm in the process, he could have saved me weeks worth of work building out relatively sophisticated algorithms that basically output useless information. So they build out the KPIs, they come up with your level of success measures that you have to hit, and then you go into the research phase. That's all just in scoping. Then you go into the research phase. You have a pretty strong pairing relationship going on between the data engineering group and the data scientists, and they review existing literature. This is all going to sound very familiar to all of you that do research. They're going to review the existing leadership literature review, and verify that they're not like reinventing the wheel here, and they're actually expanding the knowledge associated with this and developing something that's going to have some usage for the world at hand. Because if it doesn't, what you build is essentially a product or research that nobody cares about, right? If you're not breaking new ground, you're not really adding any value. So this is usually when the initial proof of concept, just a quick and dirty version, is this even possible kind of version of whatever service it is that is created. So this would be in the scientific process, kind of like the initial smoke tests survey form, like 5-question. Before you send them the 150 form question, you send them 5 questions. Like, does anybody even care about this? Here's a website. Does this look right to you? Is this going to serve any actual function for anybody in your field? And you would send this to other product people and they would verify it. So again, you bounce it back up to the product guy. Once you have this validity tech check kind of in place, they review the proof of concept, and ignore these timelines down here. This is assuming you're doing just the algorithm development. All the other things are in place. So scoping, they sign off on it. They say, hey, this looks good. This looks like it's going to serve our purpose. It's got a lot of promise. So then it flows back over and you begin this march towards a fully functional system. And it starts with the data engineering group, primarily. Now, there's a little bit of that goes on in parallel, but you can't really start iterating through your statistical models or your AI models until you have a standard, consistent, and trustworthy delivery of the data associated with that product. So it doesn't work very well for one-shot, one-time analysis. If you have a system or platform that's got a consistent data flow going through it that you can you're using for auto classifiers, or you're using for driving cars, there's a consistent set of data that's coming in from the sensors associated with all these automated cars, and they take all that data and they aggregate it and clean it, and they incorporate any kind of new scenarios into their algorithm development. But the format and structure of how they build those self-driving car algorithms stays the same. They're not changing the specification for what is available for model development very often. In fact, almost never. Most of the sensors are fairly fixed. So the data engineering organization puts together the standard data set for algorithm development, and then the data scientist really gets to work at this point. And they split their data from training to validation, and then they spit out some algorithms, and then they compare it to their acceptable thresholds of accuracy and whatever bars they've kind of set for themselves. And they iterate through this process until they get an acceptable level of accuracy and consistency and generalizability. And once they get to that point, they float it back up to the product manager again. As you can see, like, most of this flows through checkpoints with a sanity check of somebody who is thoroughly familiar with the product and the service that is trying to be developed and the needs that it's fulfilling. Because oftentimes the data scientist is not that guy, and oftentimes the data engineering is not that guy. It might be very specialized. So it's important to keep this expert involved in it. They validate it themselves, give it a smoke test, double check everything, make sure it's working the way they expect it to work, and then you'll flow it out to deployment. This is where things get a little bit bizarre for data scientists and data engineers. There's commonly people think that they deploy to production and their work is done. At that point, it's the role and responsibility of operations to kind of monitor and make sure that the system stays up. But it's a little bit more than that. The data scientist is not out of the woods at this point. Should be actively involved in monitoring the accuracy of that product that's been deployed. Obviously, out here, it's making money at this point. The product manager and the experts are happy because they're using it. But the risk that you run if you don't keep that data scientist involved in actively monitoring the health check on the accuracy and dependency of the actual algorithm, not just the system itself, is you'll get drift in the algorithm over time. So if you've ever built any sort of like auto classifier or recommendation system, you've seen this probably, is that over time, the accuracy gets lower and lower and lower, or higher and higher and higher. And if you're not actively retesting and redeveloping and redeploying newer versions of the model, that health check on that algorithm basically is telling you that it's becoming less and less effective. Now, this is common practice in stock markets, but it's so like if you build an algorithm for stock trading, eventually all algorithms associated with stock trading basically become progressively less lower return on investment over time. So basically people pick up on your strategy and then they start to duplicate it. And then as a result, it starts to become less effective because it's competitive nature of the algorithm development there. But the strange thing is you see it in pretty much every single other methodology associated with auto classifiers, primarily because the auto classifier is kind of self-reinforcing in general. So for example, we built an auto classifier for clinicians for identifying outliers associated with training, right? So basically clinicians would do a review of a medical test that some other clinician would do. And the secondary verifier would say, okay, well, I don't agree with the consistency. This person's usually rates a 5 and they're rating a 7 now for some reason on these things. And then they would flag it, and then it would be reviewed with the initial physician, and then training would commence, or appropriate action would be taken. So this whole service revolved around identifying needs of the primary physician by a secondary physician. So this classifier system was built for the secondary physician to provide a recommendation based off of historical performance of the initial physician and the general criteria associated with that assessment. And what they found was over time, the recommendation would just be accepted. They started to trust this algorithm and their assessment of the initial physician, and they would just say, yeah, that sounds about right. Yeah, that sounds about right. Yeah, that sounds about right. And because the accuracy of the algorithm was based off of how often are you in alignment with the secondary physician, what we saw was a drift where the accuracy went from about 87% to 98%. And what that told us is that the secondary physicians were really just not doing their jobs anymore. They were just accepting the recommendation of this algorithm at this point. And also, as a result of that, the training data was actually corrupting the original data that was used to develop the auto classifier. So the whole point of that story is really just the fact that you can't just deploy any sort of artificial intelligence algorithm into the wild and then just let it go on its own. They will inevitably drift, either less accurate because of competition and people picking up on it, and or some other variable in the environment and reality has changed that it depended on, or people just start to trust the algorithm too much and take its recommendation. So either way is bad. If it starts to drift from its original development accuracy during this model development period, you've essentially established a poor algorithm that needs to be redesigned and redeployed. So this whole process flow in a healthy data engineering, data science organization and a consistent product that is already deployed, once you get it out there the first time, it usually, these timelines along the bottom here, 1 to 2 weeks, 2 to 3 weeks for iteration on this. So it's saying multiple times through this, but 2 to 3 weeks per iteration, and then 2 to 3 weeks per iteration on this, depending on how many times it needs to go through it, and then 2 to 3 weeks for deployment and then monitoring cycle, is pretty consistent in a healthy operational organization that has these roles and responsibilities defined, and the technology is all in place for all of this. So it takes a while to get to this kind of like timeline and iterative process, but once you get there, these timelines are pretty realistic. So that covers this process flow. I also would encourage anybody, anytime has any questions, feel free to jump in and you know, redirect me or give me commentary. So any questions at this point? All right. So this is probably the most interesting and exciting process associated with science, in my opinion, that's kind of come across in the last like 30 years. This is essentially automation of science in a specific field or specific question. And once you get to this point, these computers can identify patterns in nature that you know, you might spend years doing one iteration in a conventional scientific process. All right. So infrastructure, data science infrastructure, and data warehousing, some of these like data engineering concepts that scientists kind of aren't always privy to. So the data engineering role itself. And I stole this slide off the internet as well because I didn't do a PowerPoint or anything for this presentation. I just kind of winging it, to be frank. But I've talked about this on so many occasions. It's fun. All right, so this is pretty important conceptually from a data engineering perspective, and it's something a lot of scientists and data scientists aren't privy to because they're used to dealing with just this final step here associated with the data delivery. And they're used to working with like a curated data set that has all the anomalies either fully explained and removed or filled in. So like blank spots, nulls, NA, not available. These all have like different meanings based on the context, and not all algorithms that you use in Python or R or SAS or whatever your language of choice is handle them the way you expect them to handle them. And somebody has to do the dirty work of putting the data in the format and the structure that those systems can use. And on top of that, when you get into a multi-source system and you're gathering data from multiple locations, there's an aggregation and a cleaning and a normalization process that has to happen so that they all are kind of speaking the same language. So different formats from different systems. And that whole process associated with data collection is complicated and takes a bunch of time and effort. And you don't want to spend cycles of your data scientists kind of doing this kind of dirty munging type work unless you have to. So you might have multiple here. It looks like they have like 4 different data sources, and it looks like it's all sales, pricing, like an inventory system, and some sort of yield, probably finance. So they're basically taking these and extracting each of those systems individually and moving it from the source data system into a staging area. And this is commonly called, it's either commonly called, it's usually called raw in most data warehousing or data lake environments. So most data lakes kind of fit the field of just being a data lake. Most raw are just data lakes. Go ahead.
Is it possible to zoom in on this a little bit? I guess it would be helpful for, I think, some of the folks.
See if I can get it to do that here.
Yeah, you may not be able to, but worth trying.
I can always do this. There we go. All right.
Thank you.
There we go. That's a happy medium, I think, right? All right. Yeah, so usually there's a data lake in here before the staging area or some sort of like raw where you just drop the data in whatever format and structure it is from the source. And it used to be, everybody's probably heard the term extract, transform, and load. which is kind of the old way of doing it. And this represents more of the old way of doing it. Extracting, transforming, and then loading it into a data store. Now it's much more of a load, transform methodology. So you would extract it from the source data, drop it into a data lake, which I don't have pictured here, but I would put right there in this form. And this would be your data lake, which has just the raw data from whatever the source in whatever format and structure it was in the source, but all within a playground area for the data engineers. And then what they would do is take the data from that source and move it into a staging area via some sort of transformation to put the source data into a consistent format. So if you had 4 different inventory systems with parts in them, you would take all of those, come up with a standard structure for parts, and then take all 4 of those and move them into that new format and structure, doing whatever transforms were necessary. Once you get them into the staging area, you would move them into the data store in this consistent format, load it into there, and do whatever other potential transformations are required to normalize the data. So converting from the English system to the metric system. If you've got 2 systems that are both measuring distance, but one is in kilometers and one is miles, you do the conversion there because you don't want the data to be, talking 2 different languages based on the data point you're looking at. So you put that kind of normalized standard structure in the data store, and then you provide that as your final version of that data set that would be then leveraged by any number of users that have use for that. So down here is where you would have a data catalog, which is essentially kind of like a navigation system and inventory system for tracking what data sets are available to all the people within the organization. So one person might be doing research on leukemia and has a whole bunch of interesting data sets that are standardized and ready for usage or associated with leukemia, whereas somebody else is doing something with cardiology. And then the third guy comes along and is like, you know what, I'm doing a study that's about heart disease in leukemia. So he doesn't want to do any of that hard work around sourcing the data and doing questionnaires. He just wants to see what's out there so that he can play around with and maybe get some insights. So what he would do, this third guy, is come out here to the data catalog, look up the various values associated with cardiology and leukemia, and then pull the data sets down that he's allowed access to and start doing his research. But he wouldn't have to worry about any of these original data sources. He wouldn't have to worry about these staging areas. He wouldn't have to worry about the data collection processes. He would just reference the data catalog. And there's a number of products that do this service called like Calibra and whatnot. But the short version is it's a supplemental service and tool that sits kind of alongside this data store for final data. And then this final layer here is really about data delivery, which is for visualization. And you can ignore these suggestions here. I don't know. I'm not familiar with Talend D. SQL Server is obviously just a database, but any database could be used for the final. And then Click is just a business intelligence visualization tool like Tableau or R Shiny. There's a million data visualization tools that you ggplot in R. I'm a little biased because I'm an R person myself in Python. But the short version is this business intelligence tool will point to this final data set because it's more cleaned, normalized, standardized, consistent instead of the source data, because the source data can change structure with no warning. It might just completely go offline and disappear. There's a lot of reasons to not point your visualization and your final presentation layer back to the source system. You want to have this buffer of cleaning and standards in place for any kind of finished product. So you can use Click, you can use Tableau. Usually Click and Tableau. Another layer over here that I would add would be associated with, see if I can do this here. Oh, it won't let me. Oh yeah, I'm doing a text here. A web portal, right? So anything you log into, any sort of web portal, usually points back to this embedded Click or Tableau chart or whatever visualization operation you've done. Oftentimes, if you don't want to provide any sort of like interactive data charting kind of activities, you would just like use screenshots or images that you would embed on the portal. But that's not particularly good this day and age to handle the data that way. So this is the dirty high-level architectural diagram that I stole online and then tweaked for you guys. Any questions associated with any of this? All right.
Yeah, Ed Krieg, can you hear me?
Yeah. Hey.
Where does old data go that you don't use anymore?
It just kind of sits out here. It may not be updated. One of the key fields that's in this data store for final is last updated date. So it tells you how old that data is and how long it's been sitting there, and how often it gets refreshed is usually maintained in the data catalog. So the data catalog will have information about that data set that basically says, this is a live feed from the stock market. It's updated every 3 seconds. Or it might say this is data that was collected in 1982 by such and such professor, and nobody has redone this research since then. So use at your own risk. But it would just sit in this repository.
And there's no storage space issues, or?
It depends on what solution you pick, right? If you just pick a straight up database like SQL Server, which is why I said, you don't necessarily want to pay attention to this, then yeah, you're going to run into storage issues. If you have one database, one storage location, then you're limited by the disk space on that server. If you get into a clustered SQL Server solution, then it's spread out among all of those different servers, and there's a lot of different methodologies that they use to kind of like safeguard the data and make sure that it's redundant and that it scales appropriately in that kind of solution. And then when you move things to the cloud, it adds an extra layer of scalability and automated growth. So you're basically only limited by your budget once you go to the cloud with those kinds of services. And then on top of that, there's even more sophisticated availability and scalability solutions associated with like everybody's probably heard of Snowflake at this point, but there's other solutions out there other than Snowflake. But that is another layer on top of the cloud that basically replicates your data infrastructure between various cloud providers. So you can have Microsoft Azure, Google Cloud, and AWS all holding your data in your data store, but it's spread out across all these various data centers across various data solutions. So if, God forbid, overnight Amazon blew up, you would still be fine because your data is also on Google.
See.
Yeah, it really depends on how much money do you want to spend.
Right.
Every added layer of protection or every decimal associated with availability adds almost like a tenfold cost associated with the deployment of these services. So when you go with a single server, depending on what you pick, you can do it for probably 10 grand a year if you want to play it pretty cheap. If you host it in the cloud, you're looking at probably closer to 15, 20. If you want to turn it into a cluster, you're looking at hundreds of thousands of dollars, depending on how big you get. When you go another layer up, you can spend millions, depending on how important is your data is really what you have to ask yourself, and how much money are we making off of it. This is also, I'll highlight really geared towards products that are not real time. When you're doing real time, you really want to switch more to another layer in here that is an ESB, which is an enterprise service bus, which basically consists of a layer that as new transactions come in, it splits them and sends them to all the interested parties. So the easiest explanation of this is like stock exchanges. They have all this database infrastructure and stuff in places, but just in the interest of not having to do multiple integrations, they'll put this layer in there that say this. I'll just do a new one. All right. So you got multiple sources here. Kind of do this the quick and dirty way. So you got multiple systems here, all of which are going to send data to multiple systems over here, right? So what you do is you build an ESB for real-time transaction services. So imagine each one of these boxes is a stock exchange. You can do an integration with a direct integration, right? That basically means you build a path from here to here, a path from here to here, 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 path from here to here. You get the idea. This does not scale very well. Every single one of these, a developer has to take the time to write the code, to do the transformations associated with all of this, right? So that's a lot of work. Each one of those lines is a developer writing a bunch of code, right? Or you can create an ESB layer, and there's a number of products that do this. So, for example, there's a product called Mirth, which is like an open source product that does medical imaging, transformation, and billing for healthcare industry. So instead of doing those 50 lines of integration work that your poor data engineer ends up having to do, what you do is one per source to your ESB. Now, the ESB has a direct feed from each one of these source systems, and then all you have to do, this system needs it from all four, one integration, one integration, one integration. So you ended up doing significantly less work. So rather than doing 3 times the number of source systems, you do 3, and then the number of the source systems. So the scalability of the work drops dramatically when you introduce this layer. And on top of that, it gives you an easy place to do basic transformations that you can make this standard format fit each one of these individually. Because you know what their functions are, you know what their functions are, and you know what their functions are. You can do it one time when this thing comes in. So when you hear people talk about middleware, this is what they're talking about. Is these ESBs like Mirth.
Are you, Keith, are you familiar, this is Alan, are you familiar with Ultrix?
Not specifically, no.
Okay, I can see a lot of parallels in what you're talking about here with the data flow options available in Ultrix. And I was just, as I envision this, we're doing this right now with a lot of Excel. And we're looking to move onto something that can coordinate our workflow with fewer, as exactly as you put it, fewer codes to write. Do you have any suggestions for an ESB that is used on a small scale?
No, I mean, honestly, most of the systems I worked in were pretty high enterprise, high volume. So it was like stock exchange data earlier in my career that kind of leveraged this functionality. Because you can imagine there's tens of thousands of stock exchanges in the world. I think most people think there's like 4. There's not. There's tens of thousands of them. And on top of that, there's millions of trading firms that want that data. So the only way they could even function with this is having a high-speed ESB. And I think they used Tableau, or not Tableau, Tibco, Oracle's ESB middleware software for most of that, where I was at. And it's a pretty common one, but it's very pricey. It's very expensive. I'm sure there's free, like open source versions of it that you can use. Like I said, Mirth is specific to healthcare imaging. I don't know what kind of data you're working with, but depending on like the specific industry or the type of data you're working with, there are different solutions that are out there. And the advantage of using an industry specific middleware solution is the fact that they've already solved a lot of those like basic functional problems that industry is used to dealing with, that maybe for like Tibco from Oracle is a very generalized use ESB. It'll do everything. But the problem is that you need a advanced doctorate knowledge of like transformation methodologies and you know, architecture design to like be able to use the dang thing. So the more specific your tool is to your industry and your needs, the better it's going to be probably for your use.
Okay, thank you for the advice.
Yeah, and don't use Excel.
We're stuck there right now, but we're moving
Right.
on.
All right, well, that's pretty much all I was really planning on kind of covering for this round. But I can dive deeper at some point. If you want me to, Jay, I could probably spend a whole hour just on ESBs.
Yeah, no, it's good. I can see how that's not only an important area, but one that needs a little more discussion. But I'm definitely enjoying it. It sounds like there's a number of people on here who are really appreciating your sharing of your both experience and your knowledge. So thank you so much.
Sure.
Great.
And if anybody has any questions or things that maybe I didn't even cover that they're like, hey, maybe Keith knows this, feel free to reach out to me anytime. I'm happy to help.
Fantastic. Excuse me. Getting all choked up about your presentation. All right. Okay. Well, thank you so much. I'll open it up to the group if there's any questions or if there's any announcements or any other items to share. Otherwise, we'll give you 8 minutes back of your lunch hour so that you can enjoy what remains of this beautiful day. If you're in Cincinnati, I imagine it's beautiful elsewhere as well, but here it's pretty darn nice. And we'll end there. So thanks a bunch, Keith, and thanks to the group. And please hit him up if you have any questions, and appreciate your willingness to support all of us. Much appreciated.
Sounds good. Thanks, guys.
All right, take care. Have a great day. Bye-bye.